Good afternoon, everyone. Could you please press the thumbs up sign if you can hear me? Okay, thank you very much. Good afternoon, everyone, and welcome to the third webinar of the IMath Webinar series. Again, I am Gino Angelo Velasco, the coordinator for research of the Institute. So again, before we continue, let me remind everyone that this meeting is being recorded and being streamed live on YouTube. And the link is posted on the IMath Facebook page. So if you have questions, you can unmute yourselves or type your questions in the chat box. All right, so let us begin. We actually have two talks for today. Our first speaker is Dr. Rhea Del Fulgencio of the Differential Equations Group of the Institute. She recently obtained her PhD from the University of Rouen, Normandy, and her talk is titled Quasi-Linear Elliptic Problem in a Two-Component Domain with L1 Data. So let us all welcome Dr. Rhea Del Fulgencio.
Hello, wait lang po. Set up lang
Okay.
ako.
Tama naman po yung pagkabigkas ko ng university. Pwede na.
Okay lang po yun, sir.
Ako hindi naman. Okay.
Hindi ko rin po ma-pronounce yun. Yung Rowan. Hindi po talaga daw siya Rowan.
Ay, hindi ba?
Rowan. Ganun daw po. So, hayaan na lang po natin sila.
Hayaan na lang. Okay, sige po. Go ahead, Rhea. So, welcome po.
Okay, so, good afternoon, everyone. Thank you to Sir Gino for the kind introduction. So, for my presentation, I will present a part of my thesis. So, this is actually a chapter of my thesis, which is an existence result for an elliptic problem posed in a domain which we call two-component domain, and the given function is in L1. So this paper is in collaboration with one of my PhD supervisors, Professor Olivier Guibet of University of Rouen, so where I finished my PhD. Okay, so this is the outline of my talk. So first, I will just present the problem that we consider in this paper. So that includes the description of the domain and the assumptions that we will prescribe to our problem. And then I really like to present a couple of slides for weak data. So when I say weak data, it's just that may pertain to data which are less summable than L2, that is L1 data or maybe measure data. And also it may pertain to not globally bounded matrix fields. And then I will present our definition of a renormalized solution for our problem. I know that for some of you, this is the first time that you encounter the notion of renormalized solution. So I would really like to give a lot of details about this framework. So I have a lot of remarks about the definition. And then the final part is our existence result. So I will present our result and provide a sketch of the proof. So we'll start with the description of the domain. So omega, it is an open set which is connected and bounded in Rn, where n is greater than or equal to 2. And we denote the boundary of omega as partial omega. So here is an illustration. Okay, from that domain omega, we take an open set omega 2 with Lipschitz continuous boundary such that the closure of omega 2 is entirely contained in the domain omega. And we denote the boundary of omega 2 as gamma. And we set omega 1 as omega minus the closure of omega 2. So as I mentioned, this is the figure or a figure for a two-component domain. So the sets omega 1 and omega 2, they are what we call the components of omega, hence the name two-component domain. And gamma, as you see here, this serves as the interface between the components omega 1 and omega 2. Hence, throughout the presentation, I will usually refer to gamma as the interface. So if we have a function defined on this kind of set, then we denote by U1 and U2 the restrictions of a function U in the two components omega 1 and omega 2 respectively. And we don't expect that that a function U is continuous in this kind of domain. So that is, zoom out ko pala. That is, the values of U1 and U2 might not agree on the interface gamma. And the jump, the difference, U1 minus U2, we call it the jump on the interface. So this is the elliptic problem that we consider in this study. So it is a quasi-linear problem. So that is, the matrix field is dependent on a solution. So the first two equations, this actually, or this is your usual heat propagation in the components omega 1 and omega 2. On the interface gamma, we have two conditions. So here we have a continuous flux, and that the flux is proportional to the jump on the interface. And the proportionality is minus h of x. And on the boundary of omega, we have a Dirichlet boundary condition, that is, our solution is 0 on the boundary of omega. So what we know so far about this problem is if f is in L2 and B and H have appropriate assumptions, then we can show that there exists a unique weak solution for this problem. So this was proven by Beltran in his master's thesis. So in our study, we want to consider a larger set of data. So hence, we have the following assumptions. So the function h, which is the proportionality of the flux and the jump, this is in L infinity, and we can find a positive h0 such that h is bounded below by h0. Now for our function f, so instead of f in L2, we now consider f in L1. And for the matrix field B, so B is Karafiadori. So Karafiadori functions are functions which are measurable with respect to the first variable and continuous with respect to the second variable. And it satisfies so an ellipticity condition and this kind of boundedness condition. So note that here, B is not actually in L infinity of omega cross R. So it is not globally bounded, that is, it's not in L infinity of omega cross R, but it is bounded whenever the second variable is bounded. So due to these two conditions, that is F is in L1 and B is not globally bounded, we know that a weak solution may not exist. And in this case, we want to find another notion of solution that will provide us at least existence. So which leads us to some theory for weak data. So let's consider first a simpler problem. So that is our usual Dirichlet boundary problem posed in a one-component domain omega. So let's assume that either F is in L1 or A is not globally bounded, or maybe both. So if this is the case, similar to what I've remarked from before, a weak solution may not exist. So what notion can we consider? So we can consider what we call a solution in the distribution sense. And it is actually proven by Bocardo and Galouet that a solution in the distribution sense exists. However, Serene found a counter unique. So we found a notion that provides its existence, but we don't have uniqueness. So for PDEs, for elliptic problems, we actually want existence, uniqueness, and stability results. So there are some notions of solutions developed for these kinds of results for weak data. So we have what we call entropy solutions. This notion was introduced by Benilan et al. In 1995. SOLA, this was introduced by Dal Alio in 1996. And the framework that we consider in this study is what we call the framework of renormalized solutions. This was first introduced by Di Perna and Lyons for a first-order PDE, which is called the Boltzmann equations. And for the development of this notion, renormalized solutions for second-order PDEs, this was first done by Lyons and Mura, where in '93, where they considered an L1 data. And it was then further developed by Dalmaso et al. In 1999 for measure data. So as I've mentioned, this is just a couple of slides, a short, very incomplete history for weak data. By the way, just a remark that these three notions are equivalent in the Dirichlet, if you consider a Dirichlet boundary problem, F in L1. Okay, so now let's focus our attention back to our problem. So just to remind ourselves that this is our problem, I labeled it P. So the main goal of this study is to show that there exists a renormalized solution. So of course, before we can even show that there exists a renormalized solution, we want to define what a renormalized can define renormalized solutions, we must know some important things. So first of which is the space that we work with. So note that we expect our solution to have a jump on the interface. And in this case, we have to define a special Sobolev space, which we will call the space V. So first, we define space capital V1. So it is the set of all H1 of omega 1 functions that are 0 on the boundary of omega. And the norm in V1 is the norm of the gradient in L2. So this is a norm. So this defines a norm since we have a Poincare inequality on the space V1. So the space V, that is the space that we work with, it is the set of all functions V such that the restriction of V in omega 1 is in capital V1 and the restriction of V in omega 2 is in H1 of omega 2. And the norm on V is this norm. So we can actually show that this norm is equivalent to the usual product norm of H1 cross omega 2. However, we consider the norm on V so we consider the norm on V like this since this takes into account the jump on the interface. So we don't have that if we just consider this usual product norm. Okay, so next definition that we must have is the truncation function Tk. So the notion of renormalized solution. As a matter of fact, you will see it in the definition of the renormalized or of a renormalized solution later. So Tk of T, so it is a function in R and it is defined as this. So I think it would be better for us if we look at its graph. So this is the graph of Tk of T. So note that if absolute value of T is less than K, then Tk preserves the value of T. And when absolute value of T is greater than K, then it is either K if T is positive or negative K if T is negative. So it sorts of truncates the value of T. So this is the truncation function Tk. Okay, so this is my first set of remarks. I only have two sets of remarks. So first, since we are considering weak data, then we don't expect our solution to be in the space V. So actually, we don't expect our solution to have enough regularity to have the usual definition of a gradient and a trace. So what do we do? So in the framework of renormalized solution, the regularity of a solution is given by its truncate Tk of U. So Tk of U has the usual definition of a gradient and a trace, but still our solution U doesn't. So what we do is we follow what was done by Benilan et al. So this paper is where they introduced entropy solutions. So in their paper, they gave a definition for a gradient for a measurable function with appropriate conditions. So that is what we will do for the gradient. And for the trace, we will generalize the results done by Giben or Opeza. So here's the result. So here's a definition for a gradient and a trace for a measurable function. So for the gradient, we generalize lemma 2.1 of Benilan et al. So our assumptions is that if we have a measurable function such that tk of u is in V for every k positive, then we can find a unique function Vi. So this function Vi is defined in omega I such that, so first, this gradient is well defined since tk of u is in V. So gradient of tk of ui is that unique function Vi times the characteristic function of this set. So that should hold for every k positive. And this unique function Vi will now, so we denote it as our usual notation for the gradient, which is gradient nabla ui. So the proof of this this item is it just follows from the result of Benilan et al. So now for the trace, so we generalize proposition 2.3 of Giben or Opeza, and from that, or for the trace, we have this additional assumption that this supremum must be finite. So if that holds, then we can find a unique function Wi, which is defined. So again, this trace is well defined since tk of u is in V. So the trace of tk of ui on gamma, it is equal to tk of Wi. And again, this should hold for every k positive. And this unique function Wi, we now set it as the trace for ui. So to prove this, so actually we divide it into two cases, I equal to 1 and I equal to 2. For I equal to 1, since in their paper, they considered, so what they studied in their paper is an elliptic problem posed in a domain with holes. So we can consider omega 1, the component omega 1, as a domain with holes. So we just follow their result. Now for I equal to 2, we can't really use all the arguments they used in their paper since for I equal to I equal to 2, we have the space H1 of omega 2. And in the paper of Giben or Opeza, they used a Poincare inequality to prove the result. So for us, we must have additional arguments, which include the equivalence of the norm of the space V and the usual product norm of V1 cross H1 of omega 2. So anyway, this is the definition of a gradient and a trace for our function u. So now we are ready to look at the definition or our definition of a renormalized solution for our problem. So u is a renormalized solution of our problem if we have the following conditions. So these first two conditions are what we call regularity conditions. So that's why I labeled it RC1 and RC2 for regularity conditions 1 and 2. So tk of u must be in capital V for all k, and u1 minus u2 times tk of u1 minus tk of u2, that must be in L1 of gamma for all k positive. So these are the regularity conditions. The next conditions are what we call decay conditions. So DC1 and DC2 for decay conditions 1 and 2. So these limits must be 0 as n approaches infinity. So DC1 or this condition is also called the decay of the truncated energy. We don't have a name for the second one. And I want to emphasize now, since I will have a remark about RC2 and DC2 later, that they are posed on the boundary gamma, so on the interface. And our final condition is our renormalized formulation. So RF for renormalized formulation. So for any C1 functions with compact support, you must satisfy this formulation. And phi, so the function's phi here must be in V intersection L infinity. So we have this formulation. So my second and final set of remarks. So more remarks. My first remark is about this formulation. So we can formally, so quote unquote, formally obtain this by choosing this function as our test function for our problem P and then integrate. So I'm saying formally since we still don't know if those integrals even make sense. So later I will explain why these integrals all make sense. So anyway, that's it for now. Next, we have that if F is in L2, so F is in L2 and the matrix field B is globally bounded, then the notion of weak solution, so a weak solution exists now since L2 data and bounded matrix. So the notion of weak solution is equivalent to the notion of renormalized solution. Okay, so in the framework of renormalized solution, there are only 3 standard conditions. So one regularity condition, one decay condition, and the renormalized formulation. However, in our case, so we had a difficulty when managing the integral resulting from the boundary. So I will just show it, this one. So this one gave us a lot of headaches, even in the proof of existence and in the proof of uniqueness. So what we did is we had to add 2 extra conditions. That's why I denoted that those 2 are both on gamma. So we had to add those to be able to manage this integral on the boundary gamma. Okay. So my next remark is actually about how we show that the integrals on the formulation are well defined. So the regularity conditions are actually used to show that these integrals are well defined. And I actually want to show this. So let's take an integral from the renormalized formulation. So our goal is to show that this is in L1 of omega I. So we want to show this. So note that since support of SI, so support of S1 and S2 are contained in the set negative K to K. So this is non-zero. So since we have here SI of UI, so this is non-zero if absolute value of UI is less than K. So that's why we can write this left-hand side as this itself times the characteristic function of absolute value of UI less than K. Okay, so from this, what we do is, so since we have absolute value of UI less than K, so we replace all UIs. By the way, this times this is just the gradient of TK of UI from the definition of the gradient of UI. So these and this, we replace it by TK of UI. So note that this is bounded. So SI is C1, where we have here a bounded domain since TK is bounded. So that's in L infinity. So this one, note that we truncated the second component. So the second component is also bounded. And from our assumption, this is also in L infinity. Now, just recall that RC1, this is TK of U in V. So therefore, the gradient or this gradient is in L2. And from our assumption, P is in V. So the gradient of Phi must also be in L2. So the product must be in L1, and so this is in L1. So these arguments can also be used to show that the other integrals on the left-hand side are well defined, except for the boundary integral on gamma. So that I will show next. Now for the right-hand side, we have there just f times a bounded function. F is in L1, and then you have a function in L infinity. So the right-hand side is not a problem. So for the boundary integral, which is this, we have to use the second regularity condition, which is RC2. So before I show how we use it, I want to remark that this is actually in L infinity. So S1 and S, oh well. Anyway, so so it's in L infinity, and then H is also in L infinity by assumption. So if it's a big if U1 minus U2 is in L1, then it's simple. So we have L1 times L infinity, which is in L1. However, if we recall, RC2 is U1 minus U2 times Tk of U1 minus Tk of U2. This is in L1 of gamma. And this doesn't imply that U1 minus U2 is in L1 of gamma. So we don't have that. So what do we do instead? So instead, we consider a function theta n, which is a function in R, and we have the graph of theta n as this one. So theta n actually has a lot of important properties that are very useful in the proof of existence, uniqueness, and stability for our problem, or for a solution of our problem. So first, note that the support of theta n is negative 2n to 2n. And from negative n to n, so note that if absolute value of x is less than n, then our function value is 1. And for negative 2n to negative n and n to 2n, we have these lines. Okay, so another property of theta n is it is Lipschitz continuous, and it satisfies the following inequality. So if we take this difference, then since the support of theta n is 2n, or is negative 2n to 2n, then we can replace r and s by their truncate, so t2n of r and t2n of s. And from this definition of theta n, note that the derivative of theta n, so absolute value of theta n prime, this is less than or equal to 1 over n. So the Lipschitz constant of theta n is actually 1 over n. Hold for all real numbers r and s. So now we are ready to show that this this integral is well defined, and I will just actually show this part. So I want to show that this is an L1 of gamma. So for the other term, the arguments will be similar. Okay. So first, we write this term as this. So the main difference is we multiplied it by theta n of u1 for large enough n. And we claim that they are equal. So why can we do that? So recall that support of S1 is contained in negative k to k. So if we choose n greater than k, then if we compute for S of u1 times theta n of u1, so I'll just show this. Then if absolute value of u1 is less than n, then this is equal to 1. So if absolute value of u1 is less than n, then that's 1. So we have S1 of u1. And if absolute value of u1 is greater than or equal to n, then and we took n to be greater than k, so that means that this is equal to 0 since absolute value of u1 is greater than k. So the value is 0. So that's why we can have, or we have that they are equal. Okay, so after that, what we do is we add and subtract theta n of u2 and use triangle inequality to obtain this inequality. So we added and subtracted theta n of u2 since we want to use this inequality. So we have that, and then this theta n of u1 minus theta n of u2, that is less than or equal to, so using this, we have 1 over n times t2n of u1 minus t2n of u2. And I rearrange the terms for the first term. So this one, so I'll just write it. This one, this is an L1 of gamma by our second regularity condition. So it's just, we just choose k equal to 2n. And then this is in L infinity. So all the terms there, or all the functions, are L infinity. And then this one, so I'll just remark that this is an L infinity since S has compact support, so S1 has compact support, theta n has compact support, so U1 and U2 must be bounded so that this is non-zero. Otherwise, if U1 and U2 exceeds some value, then this value is 0. So that's why it's L infinity. So that means that this must be also in L1 of gamma. So again, the other term is similarly proved. So we can actually avoid this very long computation. So I remarked that if we have U1 minus U2 in L1 of gamma, then the boundary integral is well defined, no question. So we can actually replace that second regularity condition by this regularity condition instead for some q greater than 1. So this will imply that U1 minus U2 is in L1 of gamma, and so we don't have to use, or we don't have to do that long computation to justify that the boundary integral is well defined. And from this, we can actually remove the decay condition, the second decay condition, since it will directly follow from this. So why didn't we use this? So to show the existence of a renormalized solution with this condition in the definition instead, we have to use what we call Bocardo-Galouet estimates. So these estimates are, and they are very dependent. So they are dependent on Sobolev embedding constants. And these constants might blow up in varying domains. So why do we have a problem with that? So actually in fixed domains, such as, or studying fixed domains, such as what we did here in our paper, it's fine. So we can use this condition instead. However, for my PhD thesis, one of our goals is to show that, or is to study the homogenization of problem P. And in homogenization, we have a domain which is dependent on epsilon. And epsilon, we want it to tend to 0. So that's an example of a varying domain. So since we want to avoid that, we avoided this condition. Okay, so one final remark. I swear, I promise this is a final remark. Decay conditions. So the two decay conditions are used to show uniqueness and stability. So uniqueness is a very different discussion, and stability, it's not so long, but it will still take time. So that's why I just left it at a remark, as a remark. Okay, so now we go to our existence result. So that is, if we have our three assumptions, so assumption on H, F, and B, then we can find a solution, a renormalized solution in the sense of our definition. So for the sketch of the proof is divided into 4 steps. So the first step, problem, and show that we have a solution for that approximate problem. So first, we approximate F with functions in L2, so f epsilon, and this is possible since L2 is dense in L1. And we set b epsilon as b of x t of 1 over epsilon of t. So note that here, the second component of b is bounded, so this is actually in L infinity of omega cross r. So since b epsilon is bounded, then b epsilon is bounded, f epsilon is in L2. So if we consider this problem, so this approximate problem, so L2 data and globally bounded matrix field, then we can show, so this is the variational formulation of our approximate problem. We can show by Schroeder's fixed point theorem that this has a solution for a fixed epsilon. So you can see, for example, the result of Beltran in his master's thesis. So this is step 1. Now, second step, notice that the approximate problem generates a sequence in epsilon. So we take u epsilon as our solution for our problem, and we extract some subsequences and show some convergences. So our first goal here is to show that tk of u epsilon in V is bounded by is a bounded sequence in capital D. So to do that, we just choose tk of u epsilon as our test function in the variational formulation, and it will give us this one. So by the definition of the gradient of tk of u epsilon, so this we can write as gradient of tk of u1 epsilon, this as gradient of tk of u2 epsilon. And for this one, this is actually greater than or equal to, so we use tk is Lipschitz continuous with Lipschitz constant equal to 1. So this is actually greater than or equal to tk of u1 epsilon minus tk of u2 epsilon squared. Then this is greater than h0. So we can use here ellipticity of B to show that we have this greater than or equal to some constant times tk of u epsilon norm in V squared. So we have that. And then for this one, we just use Helder's inequality. So that is less than or equal to norm of f epsilon in L2 times norm of tk of u epsilon in V. And then we just divide both sides by norm of tk of u epsilon in V, and note that this must be bounded by M. So we have that. The sequence tk of u epsilon in epsilon, tk of u epsilon considered as a sequence in epsilon, it is bounded in V. So skipping a lot of steps and a lot of details, we can then extract a subsequence, which we still denote by epsilon, such that for some function u, we have these convergences for any k positive, which comes from a countable set. So we want k to come from a countable set since we use a diagonal process to extract this one subsequence. So we only have one sequence for every k positive. So that's why it must come from a countable set. So this function u is our candidate for a renormalized solution of our problem. And we want to show that it satisfies the regularity conditions, decay conditions, and the formulation. So from the first 4 convergences, we have the regularity conditions. So we have 2 down, 3 more. So that's why step 3 is to show that U satisfies the decay conditions. So note that from our assumptions on B and the lower semi-continuity of the convergence, of the weak convergence, we have that this is less than or equal to this limit infimum. So actually, this left-hand side, if we take the limit as n approaches infinity, then this is the quantity in the decay condition 1. So if we show that this goes to 0 as n approaches infinity, then that's that's DC1. Now for decay condition 2, we use Fatow's lemma to show that this is less than or equal to this limit infimum. So similar, if we take the limit as n approaches infinity and we show that it's 0, then we have DC2. So if we show that this goes to 0 as n approaches infinity, then we have our result. So it is actually enough for us to show that we have this limit equal to 0. And to show that, we choose this test function 1 over n times Tn of u epsilon as our test function in the variational formulation, and it will give us this. So this left-hand side is actually the term inside this limit. So if we show that this goes to 0 as epsilon goes to 0 first and as n approaches infinity, then we have our result for the third step. And for that, we use mainly Lebesgue-dominated convergence theorem. Of course, there are some other arguments to show that we have this limit. And hence, we end the third step. So the fourth and final step is to show that U satisfies the formulation. So for that, we take this test function for the variational formulation, and I will not write the resulting equation. So we want to pass the limit of that resulting equation first as epsilon goes to 0 and then as n approaches infinity. So to do that, we use mainly Lebesgue-dominated convergence theorem, and then theta n of u1, theta n. So theta n is the function I introduced earlier. So its pointwise limit is 1 in R. And the limit that we obtained from the previous step, that is lim sup equal to 0. So we use this mainly, but of course there are still some manipulations and some minor details. So that those are what we use to pass the limit of the resulting equation to conclude that U satisfies the renormalized formulation, and hence it is a renormalized solution of our problem. So this ends the proof, and this ends my presentation. Thank you very much for your attention.
Thank you very much, Dr. Fulgencio. Let us all give Dr. Rhea a warm round of virtual applause.
Thank you.
Thank you. Thank you. Thank you. Okay, so the floor is now open for questions. Do we have any question from the audience? Clarify ko lang ulit, Rhea,
Yes po.
so ito renormalized solution, nagko-coincide din siya sa weak solution kung...
Yes po. Kapag F in L2 tsaka matrix field ay bounded din. Equivalent.
Okay. So yung condition natin L1 lang yung F, tama ba?
Yes po.
Questions po from the audience? Ayan, na-overwhelm ata sila.
Sorry po, ang dami ko talagang diniscuss, so okay lang.
Hindi, interesting.
I understand.
But you're saying that that the uniqueness naman is can also be shown pero hindi na lang naano dito. Masyado
po siya mahaba. Actually, sir, yung existence paper, separate paper siya sa uniqueness paper.
Separate paper siya sa
okay. Tapos sobrang haba po nila talagang dalawa. Kaya po namin pinag-separate kasi kapag pinagsama po namin, 40 pages more than 40 pages po yung paper. So
parang sana na rin siya.
Hiwalay na lang.
Thank you. Questions po? Questions? Okay, sige. Thank you very much.
Thank you.
Pasalamatan po ulit natin si Dr. Fulgencio sa kanyang talk. It's quite interesting makita tong alternative way para makapag-kuha tayo ng solutions. Okay, so siguro at this point, maybe we can have a 2-minute break, and then we will be continuing with the talk by Dr. Rolando Perez. Break po muna tayo. So let's come back at 2:49. sige po. Let us continue. Okay, our next speaker is Dr. Rolando Perez III, or 3D, and he is from the Optimization and Approximation Group of the Institute of Mathematics. He recently finished his PhD from Université de Bordeaux, and his talk is titled Phase Retrieval for Band-Limited and Wideband Signals. So let us all welcome Dr. 3D Perez.
So magandang hapon sa inyong lahat. So thanks for the introduction, Sir Gino. So for today, I will be discussing phase retrieval for band limited and wideband signals. So actually, the talk is divided into two parts. So first, we will discuss the phase retrieval problem for the band limited case, which is a classical problem, while for the second one, we discuss the phase retrieval problem for the wideband case, which is something we have done. And we have published this, and this is actually the first part of my dissertation. So now, before anything else, let me tell you what the phase retrieval problem is. Okay, so the phase retrieval problem refers to the recovery of the phase of a function f using given data on its magnitude, mod f, and a priori assumptions on f. So these problems are widely studied because of its physical applications, where the physical quantities involved are identified by their magnitude phase. So normally, the magnitude is easily obtainable by means of detection devices, while the phase is the one which is difficult to measure. And in practice, sometimes they use optimization algorithms to obtain the phase. So in applications, the phase retrieval problem is usually applied to identify structures of crystalline or non-crystalline particles. So here, the process is done by exposing the samples to an electromagnetic wave and analyze the diffraction patterns. So normally the Fourier transform is recovered, and the magnitude rather of the Fourier transform is recovered. Then once you recover the Fourier transform, you can recover the function back by applying inverse Fourier transform. So first, now we recall that a function f is in L2 of R is said to be band limited if f has a compactly supported Fourier transform. So as you can see here, this is a band limited signal. So the Fourier transform vanishes outside a closed interval. So for the first problem we want to solve in this talk, so we have the phase retrieval problem for band limited signals. So given a band limited function f in L2 of R, we want to find all band limited functions g in L2 of R such that their moduli agree on the real line. So here f and g are assumed, of course, to be complex valued. So to solve this problem, we will need some tools, and actually these tools come from complex analysis. So first, we recall that a function is said to be entire if it is holomorphic on all of C. And moreover, an entire function f is of finite order if there exists a rho and constants a b positive such that the modulus of f is bounded by this exponential bound over here for all z and c. And the infimum of such rho is called the order of growth of f. Sorry. So we also recall that a canonical factor associated to each non-zero zeta, which is again a complex number, is given by the following here. So so we have E0 z zeta is given by this, and EP z zeta is given by this expression here for P natural number. So actually, canonical factors are used to sort of manufacture analytic functions with prescribed zeros of prescribed multiplicity. So this is actually important, well, in particular, to manufacture entire functions. So for our case, we consider this special kind of factorization called the Hadamard factorization theorem. So we recall that every entire function of finite order P can be written as follows. So you have here z raised to m e raised to pf times this infinite product over here. So here m is the multiplicity of 0 as a 0 of f. So this takes care of the case when 0 is a 0 of f. So this just vanishes when 0 is not a 0 of f. Then pf is a polynomial of degree at most p. And zf is the zero set of f counted with multiplicities. And by the way, this bracket p here just refers to the integer part of p. Okay. So as you can see here, there are two parts of this Hadamard factorization. So the e to the pf here is the non-vanishing part, while the zm times the infinite product here is the non-vanishing part. It's the vanishing part, rather. So as you can see here, we have all of these tools from complex analysis. So now, which connects these tools to our main problem situated in on the read line? So we have the Paley-Wiener theorem. So this is just another way to state the Paley-Wiener theorem, because there are actually a lot of ways to state this one. So for our case, this is the most useful, I think. So a band limited function in L2 of R extends to an entire function of exponential type. That is, it is an entire function of finite order less than or equal to 1. So with this, theorem, we can extend our functions to the complex plane and apply these results to solve our problem. So now we solve as follows. So by the Paley-Wiener theorem, so f and g extend holomorphically to C, and this equation here can be written as this one on the second one. So how do you do this? So just square, then you split, and of course it's okay to get the conjugate of x here because x here is real. So now by the extension due to the Paley-Wiener theorem, so we can just change x to z. Well, now z here is taken to be a complex number. So now we have here an equality involving entire functions of finite order. So we can use the Hadamard factorization theorem. So here we just let f and z be given as follows. So you have the Hadamard factorizations for f and g here. So where you have this constant c tilde a, b, and natural numbers k and l. So here you have here the e to the az and e to the bz here on g as polynomials of degree 1, but the constant term in the polynomial now is absorbed by the constant c and c tilde. So you have here the red parts are the vanishing parts, while the blue ones are the non-vanishing parts. So we divide the analysis into two parts. So we first analyze the vanishing parts and then the non-vanishing parts. So before we do anything first, so of course, this is what we know. F is what we know, but G is the one we don't know. So we need to characterize G from the things in F. So for example, here, we need to characterize C tilde from C because it corresponds to this part of the factorization, B to A, L to K, and the zero set of G from the zero set of F. So now for that, with that, we proceed as follows. So okay, first you have this F and G here. You just plug them in this third equation. So that you will have a long expansion, but actually it gives a lot of nice things. So for the vanishing parts, so it can be shown that K is equal to L, and the zero set of F, ZF, so union ZF bar equals ZG union ZG bar. So what does this tell us? What does this tell us? So for example, if you have a zero in the zero set of G or a zero of G, then by this equation, then you can see that that zero must be a zero of F or a conjugate of such a zero. So if you collect all those zeros and conjugates, you will generate the zero set of G. So with that, it follows that G can be obtained by changing arbitrarily many zeros of F into third complex conjugates in the Hadamard factorization of G, and the process is called zero flipping. So here, for example, you have here the zero set of F given by ZF. So we just divide it into two parts, ZF minus A and A. So just choose one set which you want to flip into to obtain the set of complex conjugates. So it's like separating them to the conjugates and the ones that you don't want to change. So now for this part in red, so we have chosen ZF minus A. So we zero flipped it. So you have this set of conjugates, ZF minus A bar. And it is now, and we just combine it with the set A to obtain the zero set of G given by A union ZF minus A bar. So now this takes care actually of the case for the vanishing parts of the function. So now with this, it's easy actually to handle the non-vanishing parts. So the substitution again from the previous slide also implies that mod C equals mod C tilde, and the real parts of A and B are the same. So of course, using basic knowledge about complex numbers, we get that C tilde is equal to eta C, where eta C is a unimodular constant. So T here is just the unit circle or set of complex numbers with modulus 1. And B is equal to A plus I gamma for some gamma on the real line. So now, just observe so far. So you have these four things in red, and these four things actually will help us completely characterize the solutions G from the known data in F. And therefore, we have this result. So this is a theorem by Akutowicz, Walter, and Hofstetter, which has been solved independently. So let F and G be in L2 of R be band limited functions such that their moduli agree on the real line. So write F as its Hadamard factorization given by this equation here. So then for all Z and C, the Hadamard factorization G is given by the following: for some eta and T, gamma and R and A contained in ZF where 0 is not in A. Of course, we remove 0 from A because the Z raised to K factor here takes care of the case when 0 is a 0 of G. So observe here just to compare. So C, then you have here eta C. So A, you have A plus I gamma. Then ZK, so of course, K was equal to L as from the previous slide. Then you have this infinite product split into two parts. So you have here the set A and the set of conjugates ZF minus A. So the conjugate is given by this in A bar. So no worries. So one might ask, how about the convergence of the infinite product of the solutions in G? Well, it converges due to a result by Titchmarsh. So this gives all possible solutions of the phase-retrieval problem. So now, as you can see here, just some observation. You have lots of choices for eta, for gamma, and for the set A. So it means that you have a large solution set. Yeah, so we will go back to that observation towards the end. So now we move on to this extension. So MacDonald in 2004 extended this band-limited case to narrow-banded signals, that is when F and G have Fourier transforms which decrease rapidly at infinity. So it means that F hat and G hat have this exponential decay here where C is positive and alpha is greater than 1. So these imply that F and G are of finite order. So since they are of finite order, Hadamard factorization can also be used. And the proof is very, very similar to the one done in the band-limited case. It's just that your polynomials just have just what they call this. The degree of the polynomial gets larger and larger, but more or less the proof is just the same. So, and the solutions also can be obtained by zero flipping as well. So now, of course, we ask ourselves, what happens to this phase retrieval problem when alpha equals 1? So now, when alpha equals 1, the functions f and g extend holomorphically to a horizontal strip in the complex plane given by SC. So the strip SC is the set of all complex numbers whose imaginary parts lie between -c and c. So since we can just extend on a strip, Hadamard factorization cannot be used. And functions with this decay condition are sometimes called wideband signals. So just to compare the narrow band and wide band cases, so as you can see here in the graph of the narrow band signal on the left, we have here a faster decay, but on the wide band case, you have here a milder decrease towards as x goes to negative and positive infinity. Okay, so now this is the second phase retrieval problem we want to solve. So given f in L2 of R with Fourier transform in this weighted L2 space, we want to determine all functions g in L2 of R with Fourier transform in this weighted L2 space such that their moduli agree on the real line. So you might ask, why would you solve it in this weighted L2 space? Well, it's because if you solve the problem in this weighted L2 space, it actually covers the case for the decay alpha equals 1. Okay, so now we present some tools to solve the problem, and like the one from the band limited case, These tools come from complex analysis as well, but it's more advanced. But yeah, anyway, so we recall the hard disk spaces on the disk. So recall that the hard disk space on the disk D, denoted by H2 of D, is defined as the set of all holomorphic functions on the disk, which satisfy the supremum condition here. And every f in H2 of D admits a so-called radial limit, f star, of e to the I theta. It is computed by taking the limit of f as the radius r goes to 1 for almost e to the I theta in the unit circle t, with f star in L2 of t and log of the modulus of the radial limit in L1 of t. So next is we recall also an analog of the Hadamard factorization on the hard disk space on the disk. So recall also that every function f can be uniquely decomposed as follows here, and this is called the inner-outer factorization in H2 of D. Here, e to the I gamma here is a unimodular constant. Bf is the Blaschke product formed by the zeros of f. Sf is a singular inner function, and OF is the outer part of f. So we recall these parts. So first, the Blaschke product is defined as follows here. It's given by this infinite product of the factors B alpha, where alpha is taken inside the zero set of f, where each B alpha is, well, this is called a Blaschke factor, is given by the following here. So when alpha is not equal to zero, this is actually an automorphism of the disk. And also, we have here a convergence criterion, which guarantees the convergence of this Blaschke product, and actually it is called the Blaschke condition. So, and in fact, this part actually takes care of all the zeros of the function f. So you can think of this as the analog of the canonical factors in the finite order case. All right. So for the next factors, so first, the singular inner part is given by SF of W. It is equal to this exponential of this Poisson integral of nu f, where nu f is a finite positive singular measure with respect to the Lebesgue measure. Again, this is a measure on the unit circle. Okay. So the outer part is determined by the modulus of the radial limit of f. It is given by this equation here. It is just an exponential of a Poisson integral of the logarithm of the modulus of the radial limits f star. So these two parts actually correspond to boundary behavior because, as you can see here, this is a measure on the unit circle, and here on the outer part, we really depend on the radial limits of f. So again, this describe the boundary behavior of our function in the hard disk space on the disk. So given these factors, this will be helpful for us to construct our solutions. But before we go to that, we need to discuss more hard disk spaces. So now we'll move on to the hard disk spaces on the strip. So let S be equal to S1 for simplicity. So it's just taking C equals 1. So it's just a set of complex numbers between whose imaginary parts are between -1 and 1. So we consider the bijective conformal mapping phi from the strip going to the disk defined by phi of z equals hyperbolic tangent of pi z over 4, and W is equal to pi over phi prime. So the hard disk space on the strip H2 tau of S can be identified to the natural analog of the hard disk space on the disk, and it is given by the following here. It is the set of all holomorphic functions on the strip with the supremum property over here. So actually, there are lots of ways to define hard disk spaces on the strip, but this is the one which is like the natural analog, in a sense that the integrand here just depends on f and on the values of on the strip alone, because some other definitions of the hard disk space on the strip has some factors here involving phi or W. So this is the best for our situation. And now, so far, we have two hard disk spaces. So now we ask ourselves, are they related to each other? Well, the answer is yes. So given here in the box, so F is in H2 tau of S if and only if W to the 1/2 F composed with phi inverse is in H2 of D. So now we have all of these tools. So like in the band limited case, we need something which connects these tools to our main problem. So in this case, actually, it is another Paley-Wiener theorem, and it is given by the following. So the Paley-Wiener theorem on the strip. So whenever f is an L2 of R, f hat is in this weighted L2 space if and only if f is an H2 tau of S. So it means that we can extend f to a holomorphic function on the strip, which has the following supremum condition over here. So with that, we are now ready to solve the problem. So we first consider the case C equals 1. So then, according to the Paley-Wiener theorem on the strip, f and g extend holomorphically to S, and you have this equation here is then equivalent to this one. So it's just the same process as the one we did in the band limited case. So I omitted the parts here, but we introduce a new notation f star. So the star is now on the superscript, okay? With the f star equal to the conjugate of f of z bar. So in the band limited case, we just plugged in everything here, right? But in this case, we're not yet done. So we proceed as follows. So first, we multiply these two functions to both sides of the previous equation to obtain this. And after that, we apply a substitution on z and z bar, which is in terms of phi inverse to the previous equation to get this equation here. F star equals G star on the disk, where F is equal to W to the 1/2 F composed with phi inverse, and G is given similarly. And by the thing in the box earlier, we know that these two functions, big F and big G, are in H2 of D. So what have we done so far? So starting from the initial problem, we went to the Hardy space on the strip using the Paley-Wiener theorem on the strip. And by using the relationship between the two Hardy spaces, we now have our problem situated on the Hardy space on the disk. So therefore, we have the following reduction. Oops, okay. So now, this is the one we want to solve right now. So given f in H2 of D, we want to find all G in H2 of D such that we have this equation on D, or in other words, mod f equals mod G for W in -1, 1. So of course, the strategy here is, well, sort of the same as from the one in the band limited case, because you want to obtain the factorization of G from the factorization of F. So of course, if you want that, you want to obtain the Blasch products associated with the zeros of G. You want to obtain the singular inner function and the outer part of G. But of course, equivalently, you need the zero set of G, you need the singular inner measure associated to G, and the radial limits of G. And all of those things will depend on its corresponding part on the factorization of F. So since the factorization is unique, so we can obtain the following equations here. So we have here BF star is equal to BG star, and the same thing for the singular inner and outer parts. So this equation here will characterize the zero sets of F and G. The second one will characterize the singular measures associated to F and G. And the third equation will characterize the radial limits of F and G. So with these three equations, we will obtain the following lemma. So this is a lemma which we shown in our paper in 2020. So first, using those three equations, the zero sets of F and G satisfy ZF union ZF bar equals ZG union ZG bar. So as you can see here, it's really the same as the one that happened on the band limited case. For the second one, the singular measures nu F and nu G associated to F and G respectively satisfy this equation here, nu F plus C star nu F plus nu G plus C star nu F. And these are measures on the unit circle T, where C is the conjugation function here. C star nu F or nu G is called the push forward measure of nu F or nu G by the conjugation function C. So what this measure does is that if you get the so C star nu F actually just gets finding the measure of the set of conjugates. So that's simply that's what it does actually. Then the radial limit satisfy this equation here almost everywhere on T. So with these three equations, we can characterize ZG, nu G, and the radial limits of G. So now we have the following sketch. So first, we have here again the first equation. This implies that ZG is equal to A union ZF bar, ZF minus A bar for some A contained in ZF. So actually, this is the one. This actually corresponds to zero flipping, and yeah, well, it's really the same situation as if you remember from the band limited case. So now for the second equation, it actually implies that nu G minus nu F equals rho, where rho is an odd real singular measure on T. So when you say the measure is rho, is odd, sorry, when you get the measure at the conjugate, it's just which is just saying that it is just the push forward measure of rho by C. It is just equal to negative of the measure. So as you can see here on the first and the third term, so the negative here is just placed outside. So to get this one, you just transpose C star nu G and nu F to the opposite sides to have this odd real singular measure. And in fact, we have an explicit construction of this measure rho written on our paper. So if you're curious, you can check that out. Okay. Next, for the third one, so it actually implies that we have this equation involving logarithms where this function log of mod of u e to the I theta is an odd real valid function of theta and integrable on T. So it is integrable because these two functions are actually integrable on T. So using the equation above and the fact that OF and OG are outer functions, we get that OG is equal to OF OU with OU star equals 1 on D. So to prove this OU star equals 1 equation here, we just used again the third equation of the previous lemma and the fact that you have this OG equals OF OU. So as you can see here, it's not U, it's just OU because we are not sure about whether U is an outer function or not. So at the very least, we can just recover the outer part of U. So as you can see here, you have three things in colored red. So you have here ZG, nu G, and OG. So this will help us construct the Blaschke product. This will help us construct the singular inner part, and the third one will help us construct the outer function, but this is actually the outer function already. So with these three working together, we have the following result. So this is a theorem we proved in 2020. So together with my PhD supervisors, I'm sorry, I forgot to mention them, Professors Jamang and Kelly. Okay, so let F be in H2 of D and write F be as its inner outer factorization, then G is in H2 of D such that mod G equals mod F on minus 1, 1, if and only if G is equal to this factorization here, up to the multiplication by a unimodular constant where, first, BG is the Blaschke product associated with the set A union ZF minus A bar for some A contained in ZF. And this actually corresponds to zero flipping. So number two, SG is the singular inner function associated with the positive singular measure nu G equals nu F plus rho, where rho is an odd real singular measure, and OG is equal to UOF, where U is an outer function in the Smirnov class, and U is equal to 1 over U star on D. So the Smirnov class actually is the set of all holomorphic functions on the disk whose elements can be written as a quotient between two bounded holomorphic functions on the disk, and the denominator in that part actually is an outer function. So now, just some observations. Again, we have here zero flipping taking place because well, the methods we did here is just the same from the one we did in the band limited case. But here you have here SG and OG also taking part of the solution, and in other words, the boundary behavior takes part of the solution. Well, it's because, of course, in the hard space on the disk, we are always particular about the boundary behavior. So it is, of course, important that the boundary behavior takes place in the solution. So in a way, it's kind of more evolved compared to the band limited case. Okay, so also you have here various choices for A. You also have various choices for Ho, and you also have various choices for U. And of course, you have lots of choices for the unimodular constant you want to multiply your solution to. So with that, we can say that the solution set is, of course, large, like the band limited case. But of course, I wouldn't end it here yet because this is just the solution on the disk. So we need to go back to our initial setting. So again, by using this relationship on the box, so for any f in H2 of D, we can obtain an equivalent unique inner-outer factorization for functions in the hard disk space on the strip H2 tau of S. And it is given by the following here. So in fact, we have explicit formulas for BF of phi, SF of phi, and OF of phi, but yeah, they are a bit long, and well, it's because of the effect of having the change of variables. So that's why it kind of looks a bit, yeah, maybe I'd say not so nice, but yeah, we have those formulas in our paper. And using this inner-outer factorization in H2 tau of S, we can translate the result from the previous slide to functions on H2 tau of S. Actually, it's almost the same, but you just have to define a Smirnov class for H2 tau of S. And finally, by the Paley-Wiener theorem on the strip, we go back to the initial setting of the problem, and that ultimately solves the phase table problem for wide band signals. All right, so before I go to the next slide, so let's just recall our observations from our solutions. So I think I have mentioned that for the band limited case and the wideband case, the solution set is very, very large. So now our goal now is to at least reduce the solution set. But now, how do we do that? So we introduce the notion of coupled phase table problems. So for complex valued f and g in a Banach space of functions, consider the following coupled problem: mod g equals f and mod tg equals mod df, where c is some transform. So t is some transform. So t can be a lot of things here. T can be your integral transform. T can be a simple dilation. It can be a restriction in the domain, or you can add more t's as you want. Really depends on the situation. So this additional assumption involving t may either lead to uniqueness, that is, the only solution you have is just a unimodular constant multiple of f, or in other words, g is equal to cf, where c is a unimodular constant. Or if not being unique, well, you can at least reduce the set of solutions. So for the band limited and wideband case, we consider almost the same situations, and we compare what's going on. So let us recall first the band limited and the wideband cases. So this is just their complex reformulations. So here we have n power of finite order, and here on the hard disk space on the strip. So here you see these red question marks. So what do we add on these red question marks? And given those additional constraints, what will be the effect on the solution set? So first, let us consider this one. When you add the fact that mod g minus h equals mod f minus h on R, where h is some fixed reference, then this is, for the band limited case, it was done by Klibanov in 1995, and for the wideband case, it was done by us in 2020. So the effect is that we have two solutions. So for the band limited case, they considered a very specific one. H is again a fixed band limited function. For the wideband case, it's more general. It just has some assumptions on H, on the analyticity of the argument of H. Sorry. So to solve this, as you can see here, you have two conditions working hand in hand. So they represent two circles on the plane, which intersect at 2 points, and these 2 points actually correspond to the solutions. Now, for the second one, we add the fact that the moduli of G and F, of the Fourier transforms of G and F agree on the real line. So for the band limited case, it was solved independently by Ismagilov and Jamin. And for the wideband case, it's something we have done. So for the effect, it is possible to construct uncountable solutions. So what does that mean? It means that you can find an F which corresponds to infinitely many G's, and those pairs F and G satisfy the coupled constraints. So this just tells us that there is a guarantee of non-uniqueness. So for this case, we considered F to be a Rees product, where a Rees product is an infinite product which can be written as a well-defined trigonometric series. So we actually use the almost the same construction for the band limited and the wideband case. Okay, for the third one, we add the fact that mod dg equals mod df, where d is a derivation operator. So d here can be the complex derivative. It can be the difference of the function from its dilation or translation. So for the band limited case, it was done by McDonald in 2004, and again for the wideband case, we did it. So the effect is that we have two solutions. So for this part, we just use some basic properties of the operator D and a nice factorization result for F and G. So actually, it turned out that the factorization property for F and G was the same for the band limited and the wideband cases. So the proof for this coupled problem is actually the same for the band limited and the wideband cases, as in 100% the same. So again, we have two solutions. Okay, for the final part, so if we add the fact that mod G equals mod F on a line or segment, so for the band limited case, it was done by Jamang in 2014, and for the wideband case, it was done by us. So for the band limited case, Jamang added the constraint on this diagonal line e to the I alpha r, where e to the I alpha r is just the alpha rotation of the real line about the origin, where alpha here is an irrational multiple of pi. And for the wideband case, which we did, we added the constraint on e to the I alpha minus 1, 1, which is just the alpha rotation of minus 1, 1 about the origin. And again, here, alpha is an irrational multiple of pi. So of course, given the suspense, I think you know the answer, you know the effect. So actually, the solution here is unique. So for this case, for the band limited case first, they use the Hadamard factorization theorem. But for the wideband case, we first proved an analogous result on the Hardy space on the disk. So in short, we used the inner outer factorization on the Hardy space on the disk. So the proof for the band limited case and the wideband case is actually the same on the first part, because you want to show that the zero sets are equal, and it makes use of the fact that the orbit of irrational rotations is not a discrete set. Okay, so for the wideband, of course, after showing the zeros, actually it's almost done for the band limited case, because that's actually the bulk of the proof, and the other parts actually will follow easily by means of a inner product on the complex plane, just the basic inner product. But for the wideband case, it's not really as easy as in the band limited case, because as you can see here, we are in the Hardy space and we are very particular with boundary behavior. So we want to show that the boundary behavior of F and G are the same. So and with that we use Fourier coefficients to show that the boundary behavior of F and G are the same. And of course, just one thing, the fact that alpha is an irrational multiple of pi is very important here to show the uniqueness. So I won't show the proof here, but if you read the results done by Jamang and what we did, it is very, very monumental to show uniqueness. And just one last remark, there is actually a result we proved that covers these two cases, and it's like the mother case of when you have these intersecting lines or segments in this manner, where the angle is an irrational multiple of pi, and the proof actually doesn't demand any factorization theorem for entire functions or Hardy spaces, and that can be a subject of another talk. So, and lastly, you can add more constraints. It is not limited to these 4 constraints. So if you're interested, you can add more. This is something you can work on, or this is something we can work on. So with that, I end my presentation. So maraming salamat po sa inyo pakikinig.
Thank you very much, Fergie. So everyone, let us give Dr. Perez a warm round of virtual applause. Thank you.
Maraming salamat po.
So ano yung huli mo sinabi kanina, kapag alpha natin ay irrational multiple of
Pi.
ano nangyayari ulit? So hindi siya nagiging komplikado masyado yung ano.
Ay, sorry, kapag po kapag...
Ano yung sinasabi mo kanina? Sorry.
Ang sabi ko kanina, kapag yung alpha po ay isang irrational multiple of pi, it is actually very, very important to show the uniqueness. Pero hindi ko na lang po siya pinakita dun sa proof. So kasi, kapag po yung alpha mo ay rational multiple of pi, tawag dito, hindi mo mare-recover uniquely lahat. May certain things ka na mare-recover, pero it's just situated on a small region. Well, of course, sa zero set pa lang papalya na. So kaya importante yung fact na alpha is an irrational multiple of pi.
And doon ba sa doon sa may nakakuha kayo ng two solutions or countable solutions. So may relation between the solutions yung yung solution niyo may parang kayo relation between the solutions kayong establish din.
Yes po. Para siyang merong multiplier na sequence of ones and negative ones yung dun sa kasi 'di ba yung infinite product pwede mo siyang masulat as an infinite geometric series. So yung constants dun sa trigonometric series may mga naka-multiply sa kanya mga epsilon n's where epsilon n's can be zeros, ones or negative ones. Parang ganoon siya tama.
And do we have any questions from the audience? May question po ba tayo? So by the way, yung kanina doon sa band limited case, nasa lang tayo, nasa R?
Yes, R lang po.
Okay. So ginawa niyo rin ba to for Rn?
Yung sa band limited case, actually, imposible ang zero flipping for R2. Yun ang sabi sa literature. Pero for the wideband case, it's something we did not do because wala kaming idea on how we deal with factorizations on when you have H2 hard spaces on higher dimensions. So nagtry ako maghanap doon pero ayun, walang magandang mangyayari. Ayun.
So, questions from the audience? Kung meron pang curiosity naman sa inyo. Okay, so kung wala, then let us again thank you again, Dr. Turley, for that nice talk. So, okay, so thank you very much to the members of the audience and again to our two speakers for sharing us your time and your research para po dito sa ating IMath webinar. So our next IMath webinar will be in so hindi kasama yung next week or kasama ba? Anyway, so let me check. Announce na lang po namin but the speaker will come from the discrete geometry and combinatorics group. Okay, so thank you very much again, and we will see you again next time. So stay tuned for the next announcement of our webinar. Okay, so goodbye. Enjoy the rest of the afternoon. Thank you. Thanks again to the speakers.